ได้มีโอกาสพิเศษนะครับที่ได้เชิญทางนะครับผู้บรรยายนะครับทาง Professor ดร. Mark Kryder นะครับมาบรรยายพิเศษวันนี้นะครับก็ก่อนอื่นนะครับก่อนที่จะถึงการบรรยายของดร. Mark Kryder นะครับเรามีความยินดีนะครับที่ขอเชิญนะครับท่านรองศาสตราจารย์ดร. ชิดเหล่าธนานะครับเป็นผู้อำนวยการนะครับศูนย์ Hard Disk Drive นะครับเทคโนโลยีนะครับที่มากล่าวเปิดงานวันนี้นะครับ
Welcome to today's special talk in data storage technology by Professor Dr. Mark Kryder. Before we hear the words from him, I would like to invite Associate Professor Dr. ชิดเหล่าวัฒนา to give an opening speech.
ตรงนี้ป่ะขอโทษนะเพิ่งทำการบ้านเนี่ยเขาเพิ่งเขียนมาให้คุณที่จริงอยากจะบรรยายสรรพคุณของดร. Mark Kryder นะแต่นี้เห็นบอกว่าประวัติเขานี่เดี๋ยวทางอาจารย์ทีนี้จะเป็นผู้บรรยายเองนะก็เลยผมเลยต้องโม้ในเรื่องที่ทุกคนรู้หมดแล้วนะก็คือเรื่องประวัติของ Hard Disk Drive แต่อาจจะพูดเป็นภาษาอังกฤษเพื่อให้ Mark Kryder เขารู้ว่าเราทำอะไรกันมาบ้างนะครับIt is quite honor a privilege for me to introduce one of the greatest professor at Carnegie Mellon. I just mentioned to him this morning that during my education at Carnegie Mellon, I was survived by eating donut in his lab. You know, every morning I turn on his coffee machine. His lab is well sponsored, so they have lots of food and donut, and you know, I'm a Fulbright, and the funding that they gave to me is quite a half price, you know, quite small. So I do not have enough money to buy food. So every morning I went to his lab and turned on a coffee machine and eat a few donuts every day. So I survived and then got PhD. His donuts are very good, very nutrition. Well, the hard disk drive industry in Thailand has been considered one of the biggest industry in Thailand. The second biggest, the biggest one is the automobile. In the years of 2009, the figure shows that Thailand produced about 260 million drives, and the sales is almost 500 billion baht. This convinced the government that they have to spend some focus and funding to this industry. Here at NASDA, in addition to the 4 national centers, namely MTech, NECTech, Biotech, Nanotech, and TMC, we also set up a small center related to hard disk drive called HDDI, the Hard Disk Drive Institute. We been in the operation for 3 or 4 years, 3 years. For 4 years during the SPA period, and right now we are on the phase 2 of SPA, Strategic Project Alliance with Industry. The Ministry of Science and Technology and the HDDI will hope that we will be able to facilitate and cooperate with the industry. We do hope that to maintain the leading position of our industry, our hard disk drive industry, we have to do 2 or 3 things at the same time. First is we have to make sure that we have enough human resources, and that's why for the past 3 or 4 years we working with all the 4 big players in Thailand to collaborate to get training from them, send some of our staff and their staff to aboard to get a further advanced training, and also we also provide some scholarships to many students at the level of university, and we also have the on-the-job training, many courses. We do hope that the thing that we been doing will help promote competitiveness of industry to this industry when have to compete with other country. This event also partially sponsored by Seagate and Western Digital Toshiba company in Thailand. And on behalf of the HDDI NASDA, I would like to thank you all the three partners that help promoting this event. So, not to spend so much time, I think we should begin with the talk. And before Professor Kryder talk, I think the issue that I hope he will touch on is the intensity, the density of the recording capacity of the hard disk drive. I used to mention to industry in Thailand that we have to do 10 terabit per square inch. And I remember that everybody laughed at me. Now I appeal to authority, which not considered professional, you know, when I have to appeal to authority, that he the one that if you read his paper, I think he talked more than 10 terabit per square inch. Okay, please, Professor Kryder.
ครับขอขอบคุณอาจารย์ชิ้นมากนะครับลำดับต่อไปนะครับก็เป็นการบรรยายพิเศษนะครับจาก Professor Dr. Mark Kryder นะครับโดยทางอาจารย์ธีรนุชจะกล่าวถึงประวัติสั้นๆของท่านอาจารย์นะครับ
Before we hear from Professor Kryder, I would like to give a little bit of introductions about Professor Kryder's background. Professor Kryder has spent over 40 years building and leading research teams in academia and in industry. After receiving his PhD from Caltech, Professor Kryder first taught and did research at the University of Regensburg in Germany. Then he led a research team at the IBM T.J. Watson Research Center before joining Carnegie Mellon University, where he also founded the Magnetic Technology Center and the Data Storage System Center. After 20 years at CMU, Professor Kryder became Senior Vice President, Research and Chief Technology Officer for Seagate Technology for 9 years. In 2007, he returned from Seagate to Carnegie Mellon University as a professor. So during the next 2 hours, you will hear from Professor Kryder. He will share with us the current trends in HAMR technology, HAMR challenges for productions, and hate media channel integrations. And most importantly, we would like to hear from him what's the future of hard disk drive be like. So please join me in welcoming Professor Dr. Mark Kryder.
Well, thank you. It's a real pleasure to be here in Thailand. I was commenting earlier that I've wanted to come and visit Thailand for a long time. And somehow, even though I spent 9 years at Seagate, and Seagate has been here in Thailand for far longer than that, I think more like 25 years, I never had a good business reason to come to Seagate, come to Thailand. You'd think maybe as CTO you'd be able to do all these things whenever you want to, but it doesn't really work that way in industry. So this is my first opportunity and I'm delighted to be here. I was fortunate to come on Saturday evening, and so I was able to experience some of the events associated with the King's birthday, and had a wonderful visit yesterday touring around, and I really appreciate all the efforts that everyone has made on my behalf. What I'd like to do this morning is sort of give you my view of, you know, the future of data storage technology in general. Most of it is hard disk drives, but at the end I'll talk about SSDs and future solid state disks technology, how I see that fitting in with hard drives as time goes forward. If you read the the press, that stock analysts and things like that, they'd have you believe that hard disk drives are going to be dead in 2 years or something, and totally replaced by flash. I don't think anyone in the hard disk drive industry believes that. I also don't believe anybody in the flash business believes that. but the stock market analysts tend to overdrive these things at various times. So I'd like to give you a technological perspective on what the potentials are for these various technologies and how they all fit together. So let's get started. Today, hard disk drives, the areal density is about 700 gigabits per square inch on the leading edge product. Super paramagnetic effects are expected to limit the ultimate density that one achieves using perpendicular recording, which is what we're doing today in the entire industry. Will probably limit the ultimate density to about 1 terabit per square inch using the technology that we have today. Now I say about, we could go a little beyond that. Maybe they'll have trouble getting there, okay? But it's going to be close to that. We can probably go a little bit further by introducing a technology known as shingled write. This is a technology where instead of simply writing an individual track and then leaving a little guard band adjacent to it and writing another track adjacent to the previous one, in shingled write, what you do is you write a track and then you come back and you write another track slightly overlapping the first track. This narrows the first track, but you can pack the bit tracks closer together. The problem with it is that it will limit your ability to do updates. Okay, if you want to do a short update of a record, you'll now have to rewrite several adjacent tracks at the same time, which means that your IOs per second are going to go down, which is not desirable, especially if what you're trying to do is compete with solid-state disks. So now, in some applications, that doesn't matter. If you're trying to build a digital video recorder, that would be perfectly okay, because a digital video recorder has very long serial strings of bits in it. You don't do a lot of random seeks. But if what you're trying to build is a system for an airline's reservation system, then you need very, very short records and need to be able to update them very quickly. And so for those applications, shingled write would not be very suitable. But the main message, I'm not going to worry about whether these short-term issues of a terabit per square inch or 1.5 terabit per square inch. You got to realize that, of course, the areal density on hard drives goes up 40% per year today, and this means that the areal density doubles in 2 years. So we're at 700 today. 2 years from now, we got to have already, be at a place where we know what the next technology is, right? We're going to be moving on to the next thing. So these are very short-term issues that will get handled by industry, and not something that one worries about at the university. Quite frankly, they will be done by industry in the most effective way. That's not the main subject of my talk. What we have to do is to try to figure out what the new technology is that replaces perpendicular recording, and we have a very short time to do it. Now, there's been a lot of work done. I don't mean to say we're just starting now. We've been working on the alternative technologies since when I was at Seagate. We began working on them in 2001. So, this next year we'll have had, Seagate working on HAMR, at least 10 years of experience. And bit pattern media also falls into that category. So there's at least a decade of history of work behind us in the industry, at universities, so forth, on what could replace perpendicular recording. And so we'll spend quite a bit of time talking about what those technologies are and trying to give you at least my perspective on the pros and cons of each one. Now, I know there are some people here in the audience from Seagate. I know there's some people here in the audience from Western Digital. I don't know what's going on in the details any longer at either of those companies. I left Seagate 3.5, almost 4 years ago, in February of 2007. And so, you know, my perspective may be different. There may be data there that I'm unaware of. All I can do is give you my most up-to-date understanding of the technology. And it is based somewhat, I have been technical director of INSIG, the Information Storage Industry Consortium, which Seagate, Western Digital, and Hitachi have supported up until very, very recently, with the goal of evaluating what technology would succeed perpendicular recording. Okay, so I think I'm as up to date as anyone who isn't within those individual companies and making those choices. The other thing, as I indicated, that is critical is that, you know, as I said, if you read the press today, everybody seems to think that SSDs are somehow going to replace hard drives very fast. That isn't going to happen very fast. You know, SSDs today are being used in some areas, notably, you know, obviously in the iPad, in the Mac Air, MacBook Air, laptop. This has a hard drive in it. You know, those applications, and also at the enterprise level to a limited extent. But if you look at the market penetration in actual solid-state disks, it's less than 5% today in terms of the market penetration. And the other thing I would comment is that you have to have a perspective on this. It's not clear to me that when someone is buying an iPad or something of that nature, that even is really, it's not clear to me that that subtracts from the total hard disk drive market. Because people who have iPads and are heavy users also store things on the cloud. And so as they do that, every time they store something on the cloud, they're putting it onto a hard disk drive in one form or another. The other thing is in the enterprise applications, most of the enterprise applications today, what they're doing is using SSDs to improve the performance of a large disk array. And what happens when you improve the performance, by performance I mean speed, IOPS, so forth. When you improve the performance of the storage system in a large computer system, what that means is that you can now analyze and access even more information than you could before. So when you put a SSD into a storage array, they don't displace disk drives, they actually make it possible for you to put more disk drives behind it and enable you to actually incorporate more storage into the overall system. So you know, it's very hard to measure what is the actual impact of SSDs on hard disk drives. They may actually be growing the market as opposed to displacing hard disk drives in that business. Okay, so those of you who know hard disk drives have seen charts like this many, many times before. It's the history of areal density on disk drives over recent time. This goes clear back to 1956, of course. But in recent time, this has been the history. Shows both the products and the areal density demos over time. And you know, on there is 700 gigabit per square inch in the present products. Now, technologies under consideration for replacing conventional perpendicular recording. There was a lot of interest 2 or 3 years ago, interest might be the wrong word, I don't know. There were a lot of proponents for discrete track recording. There were also a lot of non-believers in discrete track recording. But in the end, I think what has happened is that discrete track media recording has largely, the interest in it has largely waned. There's not a belief that this will be the next thing that one sees. The problem is that although it probably could gain you something in track density and aerial density on the disk, the gain in aerial density would probably be less than a factor of 2. And you would have to make an absolutely enormous investment, you know, billions of dollars in order to update your factory in order to do discrete track recording. And that is unlikely to happen unless that investment will carry you on to the next technology. So if the view was for certain that we were changing to bit pattern media, and you also were going to make the investment that you would use the same tools for discrete track recording and would use it for many, many generations after that for bit pattern media, then maybe somebody would make the decision to do that. Okay. But it doesn't appear that that is likely to happen at the present time. So I think that discrete track recording is probably not going to happen. Jimmy Zhu at Carnegie Mellon has been a proponent of microwave-assisted magnetic recording. Now, this is a technology which actually dates back to a patent which I have on similar technology, basically the same technology. Jimmy actually tried to patent it and passed it down to me to evaluate, and I pointed out that I'd already patented it. But the problem is that, I mean, Jimmy had done an innovation, and that was what I hadn't figured out was a clever way of actually providing the microwave field. And I should give credit to Jimmy for having realized that you could build a spin torque oscillator into the head in order to generate the microwave field on a local scale and actually do the recording. The reason, that, actually it's sort of unfortunate. Microwave-assisted magnetic recording could be a good way of going forward, in my view. But these technologies take time to develop. The idea of microwave-assisted magnetic recording is to use a microwave field to cause precession of the spins, which will make it easier to reverse the magnetization in the media. And the only problem with that is really that it wasn't started soon enough. Okay, and as much as those of us who, you know, work on technology, and I think, you know, if I look back when I was a PhD student or shortly after that, you sort of feel like all these things can happen very quickly. You have a good idea and just implement it and make it happen. I've worked on almost every technology that was potentially going to replace hard disk drives that have existed since the 60s, and hard disk drives are still here. And it's very, very hard to bring out something new and displace an industry the size of the hard disk drive industry, because they have an awful lot of motivation for making the investments that are necessary to go forward. And there are thousands of engineers working on those problems. And, you know, you have a new idea, it takes a lot of people to bring it, to make it reality. And had we started working on microwave-assisted magnetic recording 10 years ago, like we started working on heat-assisted magnetic recording or bit pattern media, then maybe it would have a chance. But I think time is just too short to actually make it happen within the next 2 years, which is really what we need. So I think it's not a good technological reason, but it's a business reason why I don't think we will see microwave-assisted magnetic recording. Now, Jimmy Zhu, who runs the center, the Data Storage Systems Center now at Carnegie Mellon, of course, would not necessarily agree with me, but I'm giving you my perspective. Shingled write, I've already talked about. I think that probably will happen. It doesn't require a whole development of a new head. The microwave-assisted magnetic recording really requires development of the spin-torque oscillator in the head, and then you got to modify the media, get it to have the right resonance frequency, the appropriate damping. It's a huge systems problem. Shingled write is fairly straightforward. Any drive company can, in principle, do shingled write. They've got to invest the engineering to do it. They got to make the decision they want to do it, but I don't think there's any question but that if they want to, they can do it. Okay, so it's, you know, and it will happen if they think business-wise it makes sense. If they don't, it won't happen. Another technology that's been talked about is two-dimensional magnetic recording, which is basically shingled write with the addition of using two-dimensional codes. Instead of encoding data only in the serial direction along a track, actually encoding data on adjacent tracks and using two-dimensional codes for the readback, the recording and the readback. The difficulty with that technology, again, is the system performance hit. Because you are recording information on the adjacent tracks as well as the one you're writing on, it means that when you update a record, you've got to update a whole, not just a sector, but a sector plus adjacent tracks and so forth. So this would be useful only for applications requiring very long records, such as digital video recorders or things of that nature. Another one which has been quite popular and is one of two that INSIC did spend a lot of time looking at, or has been spending a lot of time looking at, is bit pattern media recording. It was one of the two contenders that the major sponsors of INSIC, Seagate, WD, and Hitachi, wanted us to try to evaluate, to decide which one was the best to go forward with. Bit pattern media recording is one of the contenders, and I'll talk more about that briefly in just a couple minutes. So let me jump ahead. Heat-assisted magnetic recording happens to be my favorite for the technology, for the next technology, but you know, it isn't a shoe-in for winning this race, but I think it will probably be the one. And then, you know, solid-state disks I'll return to toward the end of my talk. So let's talk a little bit about bit pattern media recording. The problem in hard disk drives, of course, is that as we are recording at higher and higher areal densities, we are, in order to maintain signal-to-noise ratio, we have to continually reduce the grain size in the media. If you think of the media, it's made up of a lot of little grains that today are on the order of 8 nanometers in size. And a typical bit has, you know, 40 grains in it, say, something of that order. And the signal-to-noise ratio is basically correlated with the number of bits you are detecting. If you go down to 10 grains per bit, your signal-to-noise ratio is going to degrade. And today, the signal processing isn't good enough for us to read back the information using 10 grains per bit. Now, that means that we could go yet to smaller grains in principle, which is what we have been doing over time, right? But you got to realize that we go back to 1956, we were at 2,000 grains per bit, right? Today we're at 700 gigabits, 700 billion grains per bit. So the areal density has gone up incredibly, 3.5 times 10 to the 9th, 3.5 times 10 to the 8th times over that time period. And we have been decreasing. Originally, we used particles, actual magnetic particles in disks. Okay, they were pigment of particles. And then we changed to thin film disks, and we started using grains, and we've been reducing the sizes of the grains ever since. And we're getting down so small that thermal energy, Boltzmann's constant times temperature, is becoming comparable to the magnetic anisotropy energy, which is storing the information, which is holding the information in place. The problem that one runs into is we, in principle, could make the grain smaller and increase the anisotropy energy. But if we do that, we then cannot write on it. So the real limitation comes from the magnetic write fields that are available to us. Okay. And the highest magnetization materials that are, readily available and known today are alloys of iron and cobalt, and they have a saturation magnetization of about 2.5 Tesla. So we can't write on materials which have coercivities above, say 5,000 to 6,000 Oersteds. I mean, that's what it boils down to. And so what we have to do to go to higher densities is somehow we have to be able to detect grains, fewer grains than 30 or 40 or something like that, which is what we have today. Or we have to find a way of writing on much higher coercivity materials. And that is the origin of the thinking for bit pattern media is, let's keep writing the way we were, but let's now make little islands of magnetic material, which are shown up there. So if you imagine each of those little circles, think of them as a cylinder of magnetic material on the surface of the disk, then each one of those now could, in principle, be a single grain. And now all we have to do we don't have to worry about signal-to-noise ratio quite the way we used to, because now each one of those would represent a bit. And all we have to do when we read back is to decide, is the magnetization up or is the magnetization down in each one of those little islands? Okay. We know, or we'll design the system so that we know when to do the detection, and we will look when the head is over the top of the island and detect whether the field is pointing up or whether it's pointing down. That is the whole concept of bit pattern media, okay? What we're doing in this case is going to the extreme of detecting 1 grain per bit, okay? We keep in principle, what we are able to do then is, instead of requiring 30 or 40 grains per bit in order to have adequate signal-noise ratio, in principle you can think of it as being, well, gee, I just gained a factor of 30 or 40 in areal density, right, from my material. It's not that simple, okay? But in principle, that's the idea of bit pattern media. Now, The usual geometry that people have talked about is the one shown here, which has a bit aspect ratio, BAR, of 1, right? So you have equal lines and spaces. Now the difficulty with bit pattern media, of course, is that now you have to define the bits on the disk. In the past, history, the great advantage of magnetic recording has been that we did not have to define the bit. The disk is simply featureless, right? We didn't have to do lithography to define our bits. And this has been the advantage, frankly, of hard disk drives over all solid-state technologies for the last 5 decades. That's why we have a higher areal density. It's why we have a lower cost per bit. So we're now going, if we go to bit pattern media, we're now going to define the bits lithographically. Now, to minimize the technology that we need in order to, achieve a particular areal density, it would obviously be to our advantage to make the islands the same space, the same dimensions as the spaces between them, all right? Because, for instance, if you think of a terabit per square inch, that's 25 nanometers on a square bit cell, all right? So the bit cell is 25 nanometers, and if you want to minimize the lithographic resolution that you need to achieve, or you want to, minimize the difficulty of making that 25 nanometer bit cell, then you would like to use a 12.5 nanometer island and a 12.5 nanometer space between islands, right? Because that will, that means you would need 12.5 nanometer lithography. Obviously, that's those of you who know where lithography is today, that's a bit beyond where the Semiconductor Industry Association is, but nevertheless, we don't want to make it worse. So if, an alternative would be if we did a 4-to-1 bit aspect ratio, which is, maybe a little bit more akin to what we typically do in hard disk drives today, then that would imply in one dimension we would have a 50 nanometer track width, say, but that would then imply that in the linear direction, downstream, we'd have a bit length which drops to 12.5 nanometers, which means our line would now be 6 1/4, and our space would be 6 1/4 in that dimension. So we would have just doubled the difficulty of making the lithographic tool. So we would like to use a bit aspect ratio of 1 if we're going to do bit pattern media from the point of view of lithography. Right. Now, I don't know whether there are any servo engineers in the group, but if there are, you ought to be jumping up and down and saying, wait a minute, I don't want to try to do a bit aspect ratio of 1 because that'll make it much more difficult to keep the heads on track. And that's true. Okay. So these are the hinting at some of the compromises we have to make for bit pattern media. So an alternative approach that was suggested by some guys at Seagate, Hans Richter, Dieter Weller et al., was to make this not in a square array, but rather a staggered array of bits. So if you stagger them as they've shown here, then do the recording so that what you do is you use a head which spans 2 track widths, okay? And with that head, then, you can write by timing. You would write this bit, and then at appropriate time later, you could write this bit, and then this bit, and then this bit. So you basically, by choosing the timing at which you're doing your record pulse, you could write on adjacent tracks, first this track, then that track, so forth. And similarly, during readback, you could use a wider head, spans both tracks, but based on timing, you would know over which track you were located, okay? This has the advantage that it gets rid of, or at least it relaxes the lithography requirements, okay, on the width of the head that you have to make, okay? So it helps in that regard. However, it does nothing to improve the track misregistration budget, the servo, because your tracks are still equally far, it's same spacing in the horizontal direction, basically. So your variance that you can tolerate for track misregistration does not improve. And what is worse is that now your timing during the record process becomes even more critical. And that is a serious impediment. So, the main challenges and this is, by the way, Dieter Weller's slide from Intermag a couple of years ago. But he's pointing out here that if you do an areal density of 1 teradots per square inch, then yeah, it's a bit cell size is 12.5 nanometers. The pitch size is 25. If you look at 10 teradots per square inch, there's your number. You're talking about a bit size of 4 nanometers and a pitch size of roughly 8. Okay. That is actually, that's pretty aggressive. That's well beyond the ITRS roadmap for lithography. So achieving lithography at that density will be challenging. Control of position, size, and magnetic sigmas is a big issue. And synchronizing the right head to the predefined magnetic islands is a big issue, okay? And doing low-cost manufacturing is a big issue. I add to that reliable planarized head disk interface, because fly heights on hard disk drives are very small today, the order of 10 nanometers or so. But at a terabit per square inch or beyond, at 10 terabits per square inch, you probably need to be down around 3 or 4 nanometers. And that includes, that's magnetic spacing. So you've got an overcoat, a lubricant, and a fly height all buried in that. And you cannot tolerate, you could not have etched these islands of magnetic material. You cannot have, a corrugated surface over which you're flying this head and get good reliability. So you're going to have to planarize this when you're done to a, very good planarized surface. So, yeah, here's the ITRS. Well, this is 2008. I should have updated it, but it hasn't changed much. The red dot shows you where we're talking about needing the technology to be for bit pattern media, and the ITRS roadmap just doesn't get you there. Now, it's true that in magnetic recording in the past, we have always utilized lithography tools made for the semiconductor industry. Now, maybe we can use something else. Proponents of bit pattern media will argue that you can, all we need is a single mask level. We don't have to do registration, which is critical in semiconductor processing. So, you know, we'll use nano imprint technology and just imprint on top, one mask on top of the disk. And those statements are true, but it is still a challenge, and a very formidable challenge to be able to do that. The best scheme that you know, actually within NSIG, we'd sort of come to the conclusion that to develop a unique lithography tool, you could do, you know, something better than a terabit per square inch using e-beam lithography. But e-beam lithography would be far too expensive to direct write over the disk. So that's unlikely. It would even be far too expensive to write a mask, which you use 1,000 times on the disk in order to do your, make your device. So the sentiment of the, you know, drive industry, at least all the people we were working with, was it's not likely that in the next, you know, 3-4 years when we need bit pattern media, that it's going to be able to be done with e-beam lithography alone. So we probably need some form of self-assembled arrays of perhaps block copolymers in order to define the bits. And this is a diagram of a technique using block copolymers where you get self-assembly of the materials on the surface. And the problem is with self-assembly, though, you don't get concentric tracks around a disk. You typically end up with a hexagonal array, for instance. And that doesn't work very well if you want a nice circular track around the disk. So you need to find some way of defining tracks, perhaps at a micrometer scale around the disk, and then do self-assembly within those concentric tracks around the disk. And this is some work by Tom Russell at the University of Massachusetts, in which he's showing that he can get good self-assembly at the kinds of dimensions we're talking about, 10.5 terabits per square inch in this particular case, using, in his particular case, steps in the substrate, which was, you know, a sapphire thing in this particular case. But you could imagine making steps, say, with e-beam lithography or something like that in micron dimensions, okay? Using that to guide the self-assembly into concentric tracks around the disk surface. So, you know, what I would say is that sort of as of the last INSIC meeting, the view was that to make bit pattern media real in a cost-effective way, we probably need to combine e-beam lithography with self-assembled particles lithography in order to produce a nano imprint mask which could then be stamped onto the disk to provide the lithography for making the disks. Now, I alluded to this problem earlier. Let's assume that, and I think it's a big assumption. Personally, I don't believe we have time to develop self-assembly and e-beam lithography and make a manufacturing tool in the next 2 or 3 years. That's my opinion. My impression is, frankly, that Hitachi may be further down the road with nano imprint lithography than anyone else. So they may, I mean, maybe someone is further down the path than I, you know, am aware of, but at least from what I know today, I am very doubtful that we will see bit pattern media recording in production, say 3 years from now, which is sort of when we need it. Okay? So but as I said, I'm not, I don't know the details of what's going on in any of these companies, so let's assume somebody solves that problem, okay? They've got techniques for doing that, they have those things under control. The other formidable problem that exists with bit pattern media, and this is a new problem for the drive industry, I talked about the fact that we didn't require, in the history of disk drives, we've never had a patterned media before. We've always just wrote data on the